Hello, my name is Nicolas Cardoso, and today I'm going to present our work on ad hoc system management and specification with distributed Petri nets. This work is available on volume 169 of the Journal of Parallel and Distributed Computing. The work was done in conjunction with Juan Sebastián Sosa, Paul Leher, and Hiroaki Fukuda, respectively from Universidad de los Andes in Colombia, Universidad Católica del Norte in Chile, and Shibaura Institute of Technology in Japan. The main objective of this work is to take the Petri net model that has been used before for modeling concurrent and distributed systems and extend it on a setting that has not yet before, that of distributed ad hoc systems. The main idea behind ad hoc distributed systems is that devices and nodes are disconnected in time and space, presenting challenges for the communication. So whenever two devices join the same local network, they can start connecting and communicating with each other. And as the devices are no longer in the network, then they just disconnect and no communication happens between them. One of the classical examples for distributed systems is that of a ping system, in which we have two differentiated nodes, one with the behavior of a ping message and one with the behavior of a pong message. So whenever these two nodes join the same local network, then they start connect and exchange messages between them. And they will continue doing so long they are still connected. Whenever the nodes disconnect and leave the same network, then the communication between them stops. Furthermore, in this example, we can have different ping and pong messages in the same network. That means that the connection between the nodes presenting this behavior should be available for all possible other services that they can connect to. In our example, a ping node should connect with all other available pong nodes in the network, exchanging messages with all of them. So, taking this into account, our system presents two requirements. So we need to first manage the spontaneous communication between unknown entities. As we don't know which nodes are present in the network, then we will have to connect within all available nodes that one particular node can connect. The second requirement regards that we need to assure a resilient communication for the transient disconnections. That means that if the behavior of the system relies on the communication between two nodes, we need to maintain that communication consistent even when the nodes leave a particular network and that no messages are lost. To fulfill these requirements, we put forward a Petri net-based model for the specification of distributed ad hoc systems. Our model, called Distributed Ad Hoc Petri nets, or DaPNs, is based on the basic Petri net model and extended with two new elements: the remote interfaces places and the remote transitions, PE and FR respectively. The Petri nets are basic Petri nets defined for each particular node, as shown here for the ping example. Whenever these nodes join the same local network, then the remote transitions are created between the nodes, shown here in blue. These remote arcs join one transition defining the transition ID and a service name with a remote interface, which is defined by a place with its ID and presenting the same service name as the transition. Whenever the situation happens, then we have a remote arc between the transition and the place. Both places in this example are remote interfaces, presenting the ID of the place and the remote interface to connect to a particular transition and be able to receive messages from that. To tackle the first requirement, the first thing that we need to do is to be able to compose the Petri nets defined in different nodes whenever they join the same local network. Whenever a node joins the network via the join predicate as shown here, then the composition takes place to remote arcs. So The definition of the remote arcs takes a remote transition, so a transition with a transition ID and a service name, and maps it to all the other places which have a place ID and the same service name as declared by the transition. This will happen for all transitions fulfilling this situation, defining arcs to all different service remote interface places, presenting the same interface. Once the Petri net is composed, then the behavior of the Petri net works as the regular Petri net semantics in the Petri net-based model. Then, as a node leaves the network, all remote arcs are removed from the network and the node disappears, generating a new composition of a complete DaPN in the local network at that moment in time. With respect to the second requirement, we need to make sure that the communication between the different nodes is reliable and no messages are lost. So whenever a particular node disappears, as in this example, we do with node 2, then the behavior needs to take into account that the messages sent to that node will not be lost. So whenever the node disappears, we need to make sure that the behavior of the transition in the slide is not going to change. That means that the message will be eventually delivered. To do this, in this particular setting, we introduce a special placeholder called a sentinel, so that locally the transition behaves as if it was connected to a remote interface node. Here, to do this, we define a mailbox with each sentinel storing all the messages sent by the transition, so that whenever a node connects to the network and we recompose the full DaPN, the messages are sent to that node. In particular, we can send these messages to all possible nodes with the remote interface that we desire. So if two instances of the POM node connect, then we are going to forward the messages to each of them, and the behavior of the Petri net will continue. The validation of our approach is based on 3 properties. We need to ensure that the Petri nets defined by DaPNs follow the normal Petri net behavior. We need to demonstrate that Petri nets are able to connect between nodes or nodes in the system, and we need to make sure that the messages exchanged through the net can manage disconnections. So for the evaluation, we implemented the DaPN model using Go, following the definition of the Petri net's kernel, extending it with the 2 new entities, remote arcs and service nodes. We extended the implementation using the slot library to manage the zero-config communication protocol. For our evaluation, all experiments are implemented using Docker images and they are deployed on a Kubernetes cluster. And all experiments are also defined using 3 physical nodes, all connected to a single local access network. As an example of evaluation, we take the example of a vehicular ad hoc network. In this network, we have vehicles connecting to different roadside units, exchanging information between the vehicle and the roadside unit, and this information is gathered from different ISM nodes. Then, as vehicles connect to a particular network, they will send all collected information to the RSU, and the RSU will process it and send back all information gathered until that moment in time. In our setting, we have 5 different RSUs and 2 different vehicles. As shown here in the slide, the RSUs are placing the road from 1 to 5, and the vehicles have a particular tag name, named Brian and Dom in our example. As the vehicles pass by the different RSUs, they send information to the RSU, which can be processed. And in turn, the information from the RSUs is going to be sent back to the vehicles. So if the 3 properties that we want to evaluate succeed, then we will see the information exchange between all RSUs and the different vehicles. The setting of our model is shown as follows. We will have m different ISMs generating information and sending it to vehicles as they connect to each vehicle. The vehicles, in turn, will receive that information whenever they connect to an ISM or to multiple ISMs and commit it to its database. In the database, the information is processed. Whenever the vehicle connects to an RSU, it will send that processed information to the RSU. The RSU, in turn, will receive the information, commit it to its database, and process it over there, pushing back the processed information to the connecting vehicles. The results of our example here show the flow of the information throughout time. The first two horizontal lines in the graphs correspond to the two vehicles, Brian's vehicle and Don's vehicle. And the following 5 lines correspond to the 5 RSUs in our example, moving from 5 to 1 as we go down the graph. As we can see, the information effectively moves from each of the generating cars. In the left-hand side, we have Don's vehicle generating information, passing it through the different RSUs, and that information eventually reaches Brian's car. On Brian's vehicle, on the right-hand side, we have a similar situation where Brian's vehicle starts generating the information which connects to the different RSUs as we move through time, and this information effectively reaches Don's vehicle when it connects to a particular RSU. A similar analysis can be made for the information exchanged by the RSUs. So in here, we have the information generated by each of the RSUs, and we see how this information is transmitted to the different vehicles, and it eventually reaches some of the other RSUs as the cars are connecting with those RSUs and sending the information forward. To start with the conclusion, in this presentation, we showed the basics of the model and one example of our validation. In the paper, you will find further validation of our approach, and in particular, the full formalization, all the detailed information comparing our approach with the state of the art, and the full evaluation consisting of three case studies coming from different application domains, specifying in each of the case studies which particular properties of the system we are trying to validate. To start with the conclusion then, let me take you back to the objective of this model. So we want to define a formalization for ad hoc distributed systems based on Petri nets. But we don't have to have this formalization just to have a formalization. The purpose of this formalization is to be able to analyze the system for different properties that we would like to have, such as liveness or reachability. A first approach to do this will be to apply the existing verification techniques in the Petri net model to our distributed ad hoc Petri nets. To do this, we will have to do it at each particular moment in time where we have a DaPN completely composed. However, a more interesting approach will be to develop incremental verification techniques to be able to reuse the information that we can analyze from a particular node in the DaPN, and then reuse this information for further verification whenever we compose the full DaPN. So, in conclusion, we want to highlight the 3 main properties of our approach, which is an effective formalization for the specification of distributed ad hoc systems based on a Petri net model. This model allows us to manage the runtime execution across different nodes, where we can connect and communicate with different nodes available in the network without any previous knowledge of the nodes in that network. So the connection is actually spontaneous. And furthermore, this model allows us to maintain node communication consistent even in the face of transient disconnections. So if you have any questions about our work, feel free to contact us through email or any of our digital channels.